Hi, my name is Nilesh Ramganam, and my project for advanced topics is enhancing graph neural networks for material discovery through probability-based loss function. I will first introduce the density functional theory and how it has been widely used in the field of quantum chemistry. Then I will move toward explaining how machine learning, especially graphical neural networks, is now being used in quantum chemistry. I will then introduce the Open Catalyst project and dataset, which was made in the idea of facilitating the development of new chemical compounds. Then, I will talk about the main aspect of this project, which is the probability loss functions. I will then explain how we implemented these functions and discuss about the results obtained. The density functional theory, also known as DFT, was introduced by Kong and Hodenberg in 1964. It was used to model the electronic structure of an atom. This work received a Nobel Prize in 1998 in chemistry and then has been widely used in the field of quantum chemistry. The DFT is a complex mathematical function which expands on the quantum mechanics of probability density function. However, there is a main limitation with DFT, which is it has a high computational complexity of O of n cubed. To give you just a rough idea, a molecule of 9 atoms can take around 3 days to run on a regular PC nowadays. Scientists have therefore turned towards new method of performing quantum chemistry, namely adopting machine learning, especially graph neural networks. Two works especially stand out, which is the Neural Message Processing for Quantum Chemistry by Glimmer et al. In 2017 and SHINET by Xu et al. Also in 2017. This project will use the SHINET GNN architecture introduced by Xu et al. In 2017. This SHINET applies a convolutional layer to a grid of atoms in a molecule. The SHINET mainly comprises of 4 main components, namely the molecular representation, the atom-wise layer, interaction blocks whereby message processing occurs, and a filter-generating network which applies the convolutional layers. It is then summed into a single molecular feature vector and fed to a fully connected layer to predict energy. Forces is then predicted as derivative of the energy. The Open Catalyst project was created in the aim of facilitating the development of catalysts. It has a huge focus on GNNs and uses already established models such as SHINET and DMINET to predict properties such as absorption energy and forces, which are crucial for the discovery of new catalysts. It also introduces a new dataset, which is superior to the previously introduced QM dataset. It has millions of data points, which is useful for training and validating machine learning models. This project is also open source, which facilitates the advancement of quantum chemistry and can be accessed by anyone to make an impact on material discovery. Today more than ever, we need to know how certain a model is about its prediction. This is because models are now deployed in real-life situations and can have life-impacting decisions, for example in the case of a self-driving car. Hence, probability-based loss function helps achieve that by modeling a prior distribution of the targets. This helps assess the trustworthiness of a model. The first probability-based function which we will introduce is the Gaussian negative likelihood loss. It is frequently used in Bayesian neural networks for dealing with predictive uncertainty. This loss assumes that the target follows a Gaussian distribution. Hence, the neural network is modified to predict both the mean and variance of this Gaussian distribution. This provides a way to model the uncertainty of the model's prediction. This can be useful to build a robust model and helps in better predictive capacity. The second probability-based loss function, which we'll use in this study, is the deep evidential regression loss, which was developed by Amini et al. In 2020. This assumes that the predicted mean and variance target by Bayesian neural networks contains some uncertainty, and hence this deep evidential regression loss tries to address this issue by predicting 4 parameters to model a prior distribution over the mean and predicted variance. It does so by predicting 4 parameters, which is the gamma, lambda, alpha, and beta. The gamma and the alpha parameters assumes a Gaussian distribution over the predicted mean, and the alpha and beta assumes an inverse gamma distribution over the predicted variance. This helps captures both data uncertainty in terms of epistemic and aleatoric uncertainty. A regularization term is also used to penalize the model and help prevent overfitting. And it can be seen that this unique approach provides a deeper understanding of uncertainty in machine learning models. Now we'll talk about the methodology and how the dataset was prepared. We used 50,000 samples from the OCP 200K S2EF dataset. The dataset contains 9 data points, of which 3 is of great interest to us, namely the fixed, force, and Y variables. The fixed variable indicates free atoms, the force variable is the forces per atoms, and the Y is the energy target. The data was then divided into 80%, 10%, and 10% for training, validation, and testing, respectively. In order to better visualize our data, we can use the atomic simulation environment package in Python. We can see the initial states of our atoms and then the final states of our atoms after a relaxation algorithm has been applied. The orange sphere represents copper, the gray sphere represents carbon, and the smallest sphere represents hydrogen. Now onto the model selection process, whereby we use a SHINET from the OCP repository. The SHINET is one of the lightest models and helps in faster training time. The model output was modified according to the specific loss function in use. For example, when using the Gaussian negative likelihood loss, SHINET was modified to predict 4 outputs, which is the energy, mean, the energy variance, forces, mean, forces, variance. Similarly, when using the deep evidential regression loss, SHINET was then adapted to predict 6 outputs: energy gamma, energy lambda, energy alpha, and energy beta. Similarly, this was done for the forces. Here, I will discuss how the loss function has been implemented in PyTorch. The Gaussian NLL loss is provided as a default package in the PyTorch and can be used off the shelf. Whereas for deep evidential regression loss, a custom class had to be made in order to use it. In here, we will discuss about the results obtained. This table illustrates all the energy MAE and force MAE obtained from the difference loss function. It can be seen that the L1 loss function is the one that delivered the best results, whereas the Gaussian negative likelihood loss is the one that underperformed the most, which suggests that the Gaussian distribution of the targets might not be the optimal one. This is further proved by when combining the L1 or L2 loss with the Gaussian NLL loss, which, although improved the performance, did not match the L1 loss. However, on the other hand, using deep evidential loss proved to be comparable to the L1 loss, indicating that there is potential for future exploration. In conclusion, this project aimed to compare the different loss functions which could be applied to a SHINET model in the context of quantum chemistry. The 200K S2EF OCP dataset was used for training, validation, and testing purposes. It was seen that the standard L1 loss outperformed all the probability-based loss function, with the Gaussian negative likelihood loss underperforming when compared to all other losses. This indicates that the assumption of a Gaussian distribution might not be optimal in this case. However, the deep evidential regression loss displayed some promising results, with MAE being comparable to the L1 loss. Hence, this study emphasizes on the importance of choosing the appropriate loss function. We would encourage future research to explore more about evidential deep learning and investigate on other loss functions for better handling of the OCP challenge.